In this video we will be looking at building an ammonia converter reactor, and we will be using the Gibbs free energy minimization reactor, or the Gibbs reactor. For this video we will have a feed composition containing methane, ammonia, carbon dioxide, carbon monoxide, water, hydrogen, nitrogen, and we'll use the SRK package for the prediction of the properties. Note, since we are using the Gibbs free reactor, we will not be specifying any reactions. The Gibbs reactor predicts what reactions would take place and would carry those reactions out up until equilibrium is achieved. To access the Gibbs free reactor, we need to use the function 12 key on your keyboard, and the function 12 key would bring up a palette, and this is an extended palette with all possible unit ops that Hysys has. We're interested in reactors, the Gibbs reactor. We're going to add that to our flow sheet. We're not ready to configure it as yet, and we can close our palette. To configure the reactor, we need to add a material stream. We can do this one of two ways. We can add it from the palette, which is brought up by F4 or function 4, and we can add it here, or we can add it by simply naming the streams as stream objects. So our first stream is feed, vapor, liquid, Now, some of you all may be familiar with the fact that an ammonia converter does not produce any liquids. However, we need to add a liquid stream in order to complete the flow sheet. So whether or not a liquid is produced, you need a liquid stream exiting a reactor. You will see that the molar flow would be 0, but it must be specified. So we're going to change the conditions around the feed. We're going to put in 300 degrees Celsius as the entering temperature, a pressure of 80 atmospheres, and a flow of 1000 kilogram moles per hour. Our composition will basically be a very small portion of methane, a very small portion of carbon monoxide, we will put in 0.2 or 20% ammonia. The carbon monoxide will be a very small portion, as well as the carbon dioxide and the water. The process in the ammonia production process, these chemicals are removed upstream of the converter in order that they do not affect the catalyst within the converter. The hydrogen we shall use in a 3:1 ratio. The ammonia is 0.2. Actually, let's have the ammonia be very small as well, because this is your product. And you would have some ammonia in your feed because some of the product from the reactor is recycled as feed for the reactor. The hydrogen and the nitrogen in a ratio of 3 to 1, so the nitrogen is 0.2. And we can make up the rest with hydrogen. Essentially this will be 0.877, actually 777, and there we go. So our feed is mainly hydrogen with some nitrogen and very little of the other components. It's total 1. Note that without specifying any reactions, the Gibbs reactor has solved and it has predicted an outlet temperature of 466.3 degrees Celsius. And the reason it has done that is because although you fed in at 300, is that this is an it predicts an exothermic reaction is taking place, or multiple exothermic reactions are taking place. And basically it knows that the temperature exiting based on the energy balance around the vessel will be higher. Okay, how can we know what reactions took place? Well, what we can do is come into the composition of the feed and look at it on a molar flow basis. Here we can see that there were only 10 moles of ammonia entering into this reactor. 10 moles of methane, 1 mole of the carbon monoxide, carbon dioxide, and water. If we were to do the same for the vapor stream, change its basis to molar flow, here we can see that there was a little methane produced, because this was initially 10. There was a lot of ammonia produced, and any carbon dioxide, carbon monoxide, and some of the water have been utilized. We can also see that the hydrogen and nitrogen have decreased. What has actually happened is that you have had some methanation happening with these 3 components, where methane is formed from these 3 components, and you have had ammonia conversion happening. So you've made 96 kilogram moles of ammonia. Well, actually you've made not quite 96, you've made 86. You started with 10 and you are exiting with 96.4. Note that there is no liquid present. Right, so this is at an outlet temperature of 466.3. And this is an adiabatic reactor. There is no exchange of energy with the surroundings. In fact, we can add an energy stream, R-Q, note, because we have added a variable, our degrees of freedom is now +1. We must add some information. In this case, for an adiabatic reactor, 0 kilojoules per hour. There is no exchange of energy with the surroundings. And as we expect, the temperature of the exiting stream would be 466.3. What would happen to the conversion or the equilibrium position if we were to make this reactor instead isothermal, meaning that the outlet would be exactly the same as the inlet in terms of temperature? So we would like to find out what would happen if this temperature was 300 degrees, the same as the inlet. To do this, we can delete the information provided about the energy because it's no longer adiabatic, it's now isothermal. We can come on the vapor stream and we can specify that we would like the inlet temperature to be the same as the outlet temperature. Right. So we know that ammonia conversion is exothermic, so if we remove energy, we should expect the conversion to be promoted, that there should be more ammonia produced. Initially, our inlet composition is 10 kilogram moles of ammonia. We shall now see that we are making 303 kilogram moles of ammonia as opposed to 96. This is based on Le Chatelier's principle, seeing that ammonia production is exothermic, it is promoted by a lower temperature. What would happen if we were to reduce the feed temperature from 300 to 250? Unfortunately, our system is no longer isothermal. Hysys has not determined that the feed and outlet temperature should be the same. We still have 300 degrees. It will calculate what cooling duty is required in order for us to achieve 300 degrees on the outlet, but it will not attempt to hold the outlet the same as the inlet. To do this, we can use one of Hysys's logical operations. So we're going to pull up our model palette and we're going to use something called a set block. We add the set block to the flow sheet, and to configure the set block, we want the set block to set the vapor outlet temperature as the same as the feed temperature. So we will select the target variable. In this case, the target variable is going to be the vapor temperature, and the source object is the feed temperature. Now note, a consistency error has occurred. That is because we had previously entered the information about the temperature in the vapor stream. Remember, we had set that to 300. Note it is blue. It is data entered. This consistency error shows us that the old calculation, the information we set in the vapor stream, is 300 degrees Celsius. And the set block is telling us it should be 250 degrees Celsius. Meaning that we have two sources of information for the same variable. This, of course, Hysys will alert you of and let you know that you have configured your problem incorrectly. To solve this, we clear the information specified for the temperature in the outlet stream, and we now have removed one equation or one known. You go to the home menu and notice your solver is on hold, hence your reactor is not solved. However, putting your solver on active will continue the calculations, and now the consistency error has been removed. You have removed the overspecification because we are now allowing the set block to calculate what temperature we want to hold on the outlet. We can now look at the ammonia composition. Note slightly better performance, but marginally better. There is still nitrogen present, so we have not used up all of the nitrogen there. Now, when we change the feed temperature, automatically the set block will change the vapor temperature to 275 degrees. So, in summary, when the reactions that are taking place are unknown, but we are investigating the behavior of the reactions as they approach equilibrium, or the system as it would approach equilibrium under the given temperature and pressure, we would be able to use a Gibbs reactor to do this. The Gibbs reactor will predict what reactions take place and will carry those reactions to equilibrium. Note, you can enter parameters such as the delta P for the reaction. And as you will see when we do the next video, we can actually specify reactions that the Gibbs reactor would do, or make the reactor act as a separator vessel with no reactions taking place whatsoever. The next video will cover an equilibrium reactor, in which case we will specify the components, specify the reactions that will take place, and calculate what the outlet composition from the reactor would be. That brings an end to this video.